Okay, double integrals in polar coordinates. So there are a lot of circumstances in applications where your particular application might have some circular symmetry. And in that case, it's often best to abandon rectangular coordinates and to re-express the integral in terms of polar coordinates. So we want to talk about that today with the goal really being, can you um, describe regions in polar coordinates, and then can you construct double integrals based on those regions? There are a couple of really interesting ideas. So the goals here, all the goals at the top, I want you to pay attention to. So understand the format of double integrals over polar regions, be able to execute polar integrals to also use double integrals to calculate areas and volumes. So all of those things that we learned about for rectangular coordinates, we want to be able to do those using polar coordinates. So the big idea here is that you'll remember that the the double integral that we explored in sections 1 and 2 was really just a limiting process where we were summing up columns of sort of volume underneath a surface. And what was special or interesting that you might not have noticed about that situation is we were chopping up the domain of integration in the Cartesian coordinate system. And the base of each of those rectangles was essentially just delta x times delta y, the area of the base. And then the height was just evaluate the function at some point inside the base. And that worked. And in the limit, you would get the double integral. We'd like to be able to take that same idea to polar coordinates, but the big challenge is the base is no longer a simple rectangular shape. It's now a sort of a circular wedge shape, and we've got to deal with that. So we're going to see that the area of the base of a column is now r delta theta instead of just delta x delta y. And I'll explain why that is in a minute. So, and then the last thing is we want to be able to do applications with this new integral and recognize when it's a good idea to go from polar coordinates to rectangular or vice versa. All right, so let's do a quick flyover of the textbook before we get into some of the exercises. So as I suggested, right, what we're going to do now, remember that when you take the xy plane and you express it in polar coordinates, you get one coordinate direction or one coordinate axis that's radial. It goes parallel to the r direction, and another coordinate axis that is circular. It goes parallel to the theta direction. And when we chop up the plane into a coordinate system like that, you get these little wedges, and they kind of looked rectangular, but if you really zoom in on one, you see that the outer and inner edges are curvy. They follow the arcs of circles. And then the left and the right sides are straight. They follow the rays of, of the coordinate system. What's curious about this, and you can see it in this particular picture, is here we've chopped up the radial direction in segments of equal length, delta r, and we've chopped up the theta axis or the theta direction in equal increments of delta theta. Even though we have equal increments in r and equal increments in theta, the result is that we get these different sized rectangles. A rectangle, or not rectangular, but wedge, the bases of the columns that are going to be sitting on top of these little wedges are smaller the closer into the origin that you are. You can see that here. This is a uniform delta r, uniform delta theta, and yet this wedge-shaped base at the bottom of this column is much, much larger than this wedge-shaped base at the bottom of this column. We have to account for that. It's no longer just delta r, delta theta. We've got to deal with that. The way to deal with that is to observe that we can get the area of one of these little wedges, delta A, by this formula. So if we take two consecutive, and the picture here isn't wonderful and it doesn't do a great job of illustrating this. So what I'm going to do is jump over to the notes and briefly sketch it out for you. Let me put some space. Let me put some space right here. Where am I going to put space? Oh, it was up above, yes. Okay, so in my big idea narrative, what we're talking about here are little wedges. And you may or may not know this, but if I take what's called the sector of a circle of radius r, this is called a sector. The area of the sector is given by r times, 1/2 r squared theta. That's a basic fact from geometry, and you can go look that up. All right, so we can use this formula to figure out the area of one of these wedges. All right, so let's pretend we're looking at this wedge right here. And let's pretend that it's the result of chopping up the radial direction into equal segments. So let me put an rj here. Let's say an rj minus 1. Sorry, let's not use j, let's use I. Ri minus 1, r sub I. And also, let's say that it's a result of chopping up the theta direction into, say, theta j minus 1, theta j, like that. All right, this distance right here is delta r, right, because we've uniformly chopped up the radial direction. And in fact, this angle right here is going to be delta theta, because again, we've chopped up the angular direction uniformly. So each step is the same size. But that's all we get here. Now, if we want to calculate the area of this shaded red region, we need the area of this sector minus the area of this sector. All right, so the area of the big sector, the outer sector, is going to be Ri times delta theta. I'm sorry, I keep using the 1/2 r sub I squared times delta theta. That's the big sector. And then the inner sector is 1/2 r sub I minus 1 squared delta theta. That's the inner sector. Now, if we want to know the shaded region, the area of the shaded region, then we're going to subtract these two quantities. So the area of the shaded region is 1/2 r sub I quantity squared delta theta minus 1/2 r sub I minus 1 squared delta theta. We have a common factor of theta that we can factor out along with a 1/2. And what's left behind is r sub I squared minus r sub I minus 1 squared, like that. That's the difference of squares. So we can change this into Ri plus Ri minus 1 times Ri minus Ri minus 1. All right. Now, if we agree that we're going to evaluate the function sort of at the midpoint, so if we use the midpoint rule here to figure out how tall the column is above this wedge, then that's exactly Ri plus Ri minus 1 over 1/2, right? That's exactly right here. So if we agree to use the midpoint rule, then we can replace this with r sub ij star That's the r coordinate where we're going to evaluate the function. We keep the delta theta, and this is really just delta r. So we get this convenient little formula, again, if we agree to use the midpoint rule. It's not super important that we agree to use the midpoint rule, but this is the easiest way to kind of explain what's about to happen. Going back to the text now, we end up here that the area of one of these little sectors is rij star times delta r times delta theta. It's exactly what we have here. So if we feed that into the double summation, the Riemann sum in polar coordinates, we get the height, which is the function evaluated at r star theta star, times the area of the base, which we happen to know is r star delta r delta theta. As we take the limit, what that turns into is this little factor of r right here. All right, so when we're doing Cartesian coordinates or rectangular coordinates, we don't have this extra factor of r. But when we're doing polar coordinates, if we're going to account for the variability in the size of the base of these rectangles, we have to scale delta r delta theta by another factor of r. It's kind of nice the way it works out. Just a simple factor of r. Could have been a lot more complicated, but it turned out pretty nicely. So in polar coordinates, the double integral over the region is f evaluated at r and theta, so f as a function of r and theta. An extra factor of r to account for this variability in the area of the base, and then just dr d theta. It's a double integral. If you happen to have limits, then integrating dr d theta means the inner limits are with respect to r and the outer limits are with respect to theta. Now I know you're all asking, so I'll tell you right now, it's fine to integrate in the other direction. You can integrate d theta dr. It's very rarely done, but it's a thing that you can do, and Fubini's theorem still holds here, so we can reverse the order of integration if necessary. It's not something that we're going to do in this class, but it's a thing that does happen rarely. Okay, another thing to know, if you have a Cartesian function, f of x and y, and you would like to integrate it over a polar region, all you have to do is replace the x with r cosine theta, the y with r sine theta, and the dA with r dr d theta. And that's enough to convert the whole integral to polar coordinates. And we'll do this many, many times in the exercises. A lot of this it really involves you being able to accurately describe regions of integration in polar coordinates. So it's a bit of a review of that opening chapter where we talked about polar coordinates. I'm going to kind of just review that as we go through some of the exercises. If we want to evaluate a double integral over a polar rectangular region, what does that mean? A polar rectangular region is one in which r goes from a constant to a constant and theta goes from a constant to a constant. And in such circumstances, the shapes are actually these wedges. So in polar coordinates, this is what we would call a rectangular region. It's what I call a wedge. And it's because r always goes from one fixed value to another, and theta always goes from one fixed value to another. There are more general regions that we can discuss, and the way that we evaluate them is to just take that general region. Let me back up a little bit. The technical definition is to take that general region, put a a polar wedge around it, and treat it as a rectangular a polar rectangular region. We don't need to do that in the execution. Mostly what we're interested in is describing the polar regions in terms of polar functions. So for example, let's say this is the general region. The limits, this would be a region of type 1 in polar coordinates because r goes from one function out to another, and theta goes from a constant to another constant. We can have polar regions of type 2, but as I suggested earlier, we're going to rarely encounter those in this class. It's a thing that happens, but it's not something that we do often. If it were a type 2 region, then R would be going from a constant to a constant. So there would be an inner arc and an outer arc, and theta might be a wavy kind of thing. Theta would be a function of R in that case, and you would have to swap the region of integration. You would integrate with respect to theta first and then with respect to R. As I said, we're going to always be doing dr d theta instead of d theta dr. So double integrals over general polar regions, you see R, the lower limit is a function of theta and the upper limit is a function of theta, and then theta is just between two constants. We'll see examples of that, several examples of that in a minute. Polar areas and volumes. So if you integrate a function over a polar region, what you're getting is the volume under the surface and above the xy plane. No big deal there. And if you integrate the function 1, the constant function 1, what you're going to get is the area of the polar region over which you're integrating. We'll see those in some examples as well. All right. Last thing here, I think there's a brief discussion of improper integrals over polar coordinates. We're going to de-emphasize that. If we encounter improper integrals later in the semester, I'll certainly talk about it then, but we're not going to focus on it today. So for the exercises, let's go over to our notes here and just kind of work through these one at a time. We're starting with, in the following exercises, we want to express the region D in polar coordinates. Let's look at this region D, and honestly it's not important that we understand what this region looks like, but let's do it anyway as a form of review. We're looking at the region where x squared plus y squared is less than or equal to 4x. X squared plus y squared is less than or equal to 4x. It might be useful to look at the boundary of this region in order to understand it a little bit better. So we look at x squared plus y squared equals 4x. You might be sensing a circle here, but that 4x is a little bit of a snag. How do we deal with that? You may remember that we move the 4x over to the left-hand side and complete the square. Like that. Move the 4 back over to the right-hand side. And what we see is a circle centered at 2, 0 of radius 2. So that's just a brief review. It's actually not super important in this particular case. In polar coordinates, we write the set of polar coordinates r and theta. How do we transform this condition into polar coordinates? Simply substitute x equals r cosine theta and y equals r sine theta into the expression. In this case, we recognize that x squared plus y squared is actually r squared, and the right-hand side is 4r cosine theta. We can simplify this expression a wee bit. And the condition becomes r less than or equal to 4 cosine theta. All right, simple as that. Moving on, we now have this sort of arc or arch of area in the form of D. Let's look at this and figure out what are the r and theta parameters that describe this region. So D in polar coordinates, r and theta, has to satisfy the following conditions. We see that r always goes from 3 out to 5. So a condition that certainly marks this particular set is 3 less than or equal to r less than or equal to 5. But that's not enough. If we just stop there, then we would get this whole donut-shaped figure. Over what range of values does theta travel? Well, we can see that theta is going along from here to here, and we recognize this as starting at pi over 4 and ending at 5 pi over 4. And this, in fact, gives us the limits in the theta direction. Pi over 4 less than or equal to theta less than or equal to 5 pi over 4. So there is a mathematical description of the set D. All right, here we're asked to actually evaluate the double integral over the polar rectangular region, so let's do that. In problem 38, we're given the function in Cartesian coordinates, which means we're going to have to substitute the polar conversion formulas, but we're given the region of integration in terms of r and theta, so that's convenient. Notice that the limits are constants, so this is one of those rectangular polar regions. Those are really easy to build integrals around. R is going to go from 0 to 1. Theta is going to go from pi over 2 up to pi. The integrand is going to be the cube root of x squared plus y squared, which we recognize as r squared. So this is the cube root of r squared. And the integral, because it's a polar integral, dA is going to become r dr d theta, like that. My pen is really sloppy today. I don't know why. Okay. Now it's just an iterated integral. It doesn't matter where it came from or what it's doing. We have an inner integral and an outer integral. And as is often the case, not always, but as is often the case, when you have constant limits of integration, and there's no theta here, we can actually do the theta integration first. It just introduces a constant. And how do I justify that? Because the integrand here is the product of a function solely of r and a function solely of theta, secretly 1, we can actually separate the double integral into two single integrals. So let me show you that just to justify what I'm about to do. So those are the two integrals. On the left-hand factor, we integrate 1, we get theta, we plug in pi over 2, and we get pi over 2 after subtracting. The other integral is a little bit more complicated. We get r to the 5/3 divided by 5/3, and we evaluate from 0 to 1. That looks good, just thinking a little bit. Yep, that's fine. So we plug in 1, we plug in 0, we subtract, and we get 3 pi over 10. Let me check my notes here, make sure I'm not misleading you. That looks good. Okay, so moving right along. Here's another one, same deal. We're going to evaluate this double integral using polar coordinates. Here we're actually given the entire integral in terms of Cartesian coordinates, so it's up to us to convert. And this looks wildly complicated, but it's not as bad as it might seem, and I wanted to kind of illustrate what happens with this particular quantity, the arctan. If we look at y, let me go back to black here. If we look at y, r sine theta, and x, r cosine theta, and we divide, we actually get the tangent of theta. So in polar coordinates, y over x is just the tangent of theta, and taking the arctan, the inverse of the tangent, we end up here with just theta. So as scary as that looks, it simplifies quite nicely. All right, let's build the rest of this double integral. E to the x squared plus y squared, again, we recognize that quantity, and that should be a knee-jerk reaction for you. X squared plus y squared is equal to r squared in polar coordinates. So we get e to the r squared times the quantity 1 plus 2 theta, based on our calculation off to the side there. What does dA become? dA is r dr d theta, r dr d theta, like that. And the limits of integration, r goes from 1 to 2 on the inner integral, and the outer integral pi over 6 out to pi over 3. Once again, we have an integrand that is the product of a function solely of r and a function solely of theta, so we can separate these into two integrals. The theta integral, pi over 6 to pi over 3 of 1 plus 2 theta d theta times, let me move these guys out of the way here, times the integral let's see, 1 to 2 r e to the r squared dr. Now I want to draw your attention to something else here. We see this r squared in the exponent and this r down here next to it. This would be an impossible integral if the r down here were missing. We wouldn't actually be able to do this integral. But with the r there, this is a relatively straightforward u substitution. U equals r squared, du is 2r dr, and we can carry on from there. Let's just jump over to Sage, and I wanted to kind of walk you through how to do polar integrals over in Sage. The only real difference is you have to remember to declare r and theta up here with the variable command. After that, all of the functions are the same. Let's do this first integral. So we'll show the integral of what, 1, oops, didn't want that. We'll show the integral of 1 plus 2 theta as we integrate from theta equals pi over 6 out to pi over 3. Let's see what that gets us. So that gives us 1/6 pi, 1/12 pi squared. So 1/6 pi, 1/12 pi squared. That's the first quantity. And the second quantity, which I trust that you could do by hand, but I also just want to show you this in Sage. And r is going to go from 1 to 2, I believe. Yes, so r times e to the r squared, r goes from 1 to 2, and that is 1/2 times e to the 4th minus e. 1/2 e to the 4th minus e, like that. I would probably just stop there. Don't multiply this out or do any additional work. If you need an actual number, just go ahead and stick it into Sage or your favorite calculator. All right, in the following exercises, these integrals have been converted to polar coordinates for you. Let's verify that the identities are true and then choose which of the two integrals we'd rather integrate. In other words, which of the two is easier to integrate. So we'll do both of those things. I'm going to start with the left and show you how to get to the right. I usually start with the Cartesian side because I have more sort of intuition about what graphs and functions look like in Cartesian coordinates or rectangular coordinates. Here we have y going from x squared to x, so we want to plot the function y equals x squared, which something like, well, it is this parabola, and then the function y equals x, like that. So it's this very thin piece of graph. And we're going from x equals 0 to 1. So if you smash this down, you're going to get 0 to 1 here. So we're talking about this segment in here. I'm hesitant to, well, I guess I'll shade it in. And you know what I'm going to do? I'm going to redraw this with a slightly different scale to emphasize what's happening when we integrate this region over, over polar coordinates. So I don't really know exactly the proportions of this sliver. What I want to do is kind of emphasize, make it a little bit fatter like that. All right. And I want to emphasize that when you're integrating in Cartesian coordinates, you're always integrating in vertical and horizontal slices. When you're integrating in polar coordinates, you're always integrating in radial slices from the origin, like this, or in sort of circular arcs when you're integrating with respect to theta first. Now, as I mentioned earlier, we're never integrating with respect to theta first in this class, so we're always thinking about rays that emanate from the origin and go out to some particular boundary curve, like that. All right, so the lower limit of integration for this integral, the lower limit, r is always starting at 0. The distance from the origin is always going to 0, is always starting at 0. And then it's going out to this curve. Well, let's remind ourselves what this curve is. This is y equals x squared, the parabola. But remember, we need to convert this to polar, so this is r sine theta equals r squared cosine squared theta, which we can simplify a bit by canceling one of the r's and dividing both sides by cosine squared. Sine theta over cosine squared theta equals r. Now, if you rewrite this strategically, this is sine theta over cosine theta times 1 over cosine theta, right? Just rearranging the factors in the numerator and the denominator. Sine theta over cosine theta is really tangent theta, and 1 over cosine theta is really secant theta. So in the end, what we've written is, we've written this curve as a function r of theta. R is equal to the tangent of theta times the secant of theta. So we know when we're integrating along these red rays that start at 0 and always end on the curve, we know that r is always starting at 0 and ending at tangent theta secant theta. Over what range of theta values is all of this occurring? It's happening for theta starting at 0 and theta ending at pi over 4. All right, so we have recast the limits of integration, recast the domain of integration in terms of polar coordinates. Now let's recast the integrand. We see our familiar friend x squared plus y squared, secretly r squared. 1 over the square root of r squared is just 1 over r. And then dy dx becomes r dr d theta. And this is a nice thing. The r's cancel. And we're left with this integral of the constant 1. All right, now, you don't get to do any kind of fancy separating or multiplying. And why is that? Unlike the previous integrals, we now have a theta appearing as a limit in the limit of integration. So we can't separate things, we can't simplify things. We have to go back to our old ways where we do the inner and then we do the outer. Let's do the inner. The inner is going to be 0 to tangent of theta, secant of theta of the constant function 1 dr. We anti-differentiate 1 with respect to r. We get r from 0 to tangent of theta secant of theta, like so. We plug in the top, we plug in the bottom, we subtract, and we get tan theta secant theta minus 0. Now we do the outer integral. This is more complicated than ones we've seen earlier because we now actually have a function, tan theta secant theta d theta. I don't know if you remember. This one I kind of has always stuck with me. The derivative of secant theta is secant theta tangent theta. So if I'm integrating here, the antiderivative of tan theta secant theta is just secant theta. So this is secant theta from 0 to pi over 4. If I plug in pi over 4, 1 over the cosine of pi over 4 is 1 over root 2 over 2, or 2 over root 2. If I plug in 0, 1 over the cosine of 0 is 1, and that's the outer integral, and in fact, the whole integral. Now, the last part of this question is which integral would I rather do? So I've established, I converted it, and then I did the polar integral, and I'm asked which one would I rather do? Honestly, this is going to be a really hard integral to do in Cartesian coordinates because you don't have a du. If I'm integrating with respect to y, I have a square root of x squared plus y squared. I've got this y squared underneath the square root, but I don't have a nice accompanying du to do a u substitution. So I'd probably be stuck with a complicated trig substitution, which I'd rather avoid. On the other hand, when I converted this over to polar coordinates, I got a relatively easy integral. So here's another motivation for converting from Cartesian to polar. Sometimes an integral that's really hard to do in Cartesian is pretty straightforward in polar. Here's an example of that. Okay, here we're asked to convert the integral to polar coordinates and evaluate it. So let's do that. The first thing you want to do always is sketch the region in Cartesian coordinates. So we've got this region. Let's figure out what it looks like in Cartesian coordinates. Here we're integrating with respect to y on the inner integral. So this is y equals up to y equals. If you look at that equation closely, y equals 16 minus x squared. You square both sides. You move the x squared over to the left-hand side. You immediately see that this is the equation for the circle of radius 4. Like that, pardon my drawing. And we're integrating from the bottom to the top, so we're integrating in Cartesian coordinates from here up to here, and we're integrating over this part of the x-axis from 0 to 4. So this corresponds to essentially this region. Now that we've identified the region, it's up to us to re-express it in polar coordinates. So let's do that. I'm going to re-sketch this because the other one's a little bit messy. And we're interested in the right half of this circle of radius 4. Here, radius 4. Remember how this works. We're going to integrate with respect to r, which means we're taking r from the origin out to the curve. And not only is that happening up here in the first quadrant, but it's happening down here in the fourth quadrant as well. Now, if I want all of these rays to cover completely this shaded region above, if I want the rays to cover completely the shaded region above, over what range of theta values do I have to cover? I need to go from minus pi over 2 up to pi over 2, or any other angles that cover that same stretch. So I kind of have things under control now. The polar integral, r is always starting at the origin and it's going out to this curve. What is this curve right here? This is r equals 4. It's just the curve r equals 4. All right, and the theta limits go from minus pi over 2 up to pi over 2. The last thing we want to do is deal with the integrand. Sine of, and there's our old friend, x squared plus y squared, sine of r squared, and then dy dx becomes r dr d theta. Okay, you'll notice a lovely thing has happened here. Once again, sine of x squared plus y squared, that would have been hard to integrate. I don't have a handy du sitting around. But when I convert to polar coordinates, I still have an r squared inside the sine, but now I get this extra factor of r from the polar coordinate transformation, and lo and behold, I get a convenient du. All right, so this is a separable integral. The theta and the r integrals can be separated out, and in fact I can just do the theta integration right away. If I integrate this thing with respect to theta and go from minus pi over 2 to pi over 2, I'm going to introduce a factor of pi, and what's left behind is the integral from 0 to 4 sine r squared r dr. I want you to get used to doing these kinds of shortcuts. They can save you a lot of time. Okay, we can do a u substitution here. U is equal to r squared. Du is equal to 2r dr. We can transform this integral, pi. Let's see, r dr is 1/2 sine of u du. And when r is 0, what's u? 0. When r is 4, what's u? It's 16. Now we're ready to do this integration, pi over 2. Anti-differentiating sign with respect to u is minus cosine of u, evaluated from 0 to 16. This turns out to be pi over 2 times the quantity, 1 minus cosine of 16. Let me check my notes, make sure I'm not lying to you. That does look good. Okay, and you could punch that in again. Punch that into Sage if you want an actual numerical answer. Moving on to 158. Determine the average value of the function x squared plus y squared over the given region. All right, this is a relatively straightforward question, but I noticed that this figure leaves a bit to be desired. This is a very misleading figure, and I've informed the authors that they should probably tweak it a little bit. This seems to be a polar graph with a polar coordinate system overlaid, but if you look closely, you'll see that the scale in the y direction is different from the scale in the x direction. This is a distance of 0.1 right here. This is a distance of 0.2 on the same circle. So this is a typo, in my opinion, and you should be aware of it. So these are not actually circles. These are sort of some kind of weird ellipse because the author didn't give it a 1-to-1 aspect ratio. And this is secretly a 45-degree angle right here and here, not this thing. So we can actually replot this over in Sage and ensure that there's the correct aspect ratio. Let me show you how to do that here. So we'll use the plot command, and the plot command is able to take a function r as r is a function of theta. So we're going to plot cosine of 2 theta, and we're going to plot it over the range theta from minus pi over 4 to pi over 4, minus pi over 4 to pi over 4. But we're going to feed it the additional option that this is a polar plot. So we'll say polar equals true. And we're also going to set the aspect ratio to be 1. And with all of that in mind, we'll get a nice polar plot. Now we see that the distance from here to here, from 0 to 0.2, is equal to the distance from here to here. And in fact, we also see that the angle looks more correct. So let me grab a copy of this and let's paste it into here. I wonder if it'll let me paste it right here. Yep. All right, and this is much, much better. Now we see that those angles are indeed 45 degrees, and these circular arcs kind of look like this. All right. Okay, so much, much better representation of the figure. All right, how are we going to integrate this thing? We're looking to find the average value of this function over the region D. So the first thing is to build the limits of integration of this polar integral. Remember that when you're doing polar integration, you're integrating in the radial direction first. So you're starting at the origin and going out to the curve along rays like this. This curve is r equals cosine 2 theta. So the integral goes from 0 to 2 cosine theta. And over what range of theta values do we have to take these rays? The first ray starts at minus pi over 4 and the last ray ends at pi over 4. So the limits in the theta direction are minus pi over 4 to pi over 4, like that. The function x squared plus y squared, we've seen this guy several times now. That's r squared. And then the area dA is just r d theta. But we need to find the average value of this function. So that means we actually have to divide by the area of this region right here. What's the area of this region? Well, we're going to need another integral for that. But this integral is a little bit simpler. We integrate from minus pi over 4 to pi over 4, from 0 to 2 cosine theta. Notice those limits of integration are the same, but the integrand is the constant function 1, r dr d theta. Don't forget the r here. That goes along for the ride. Okay, well, once again, we see this function. We might be tempted to separate it into an integral of r and an integral of theta, but we cannot do that because we have a theta appearing up here as a limit of integration, so we cannot separate either of these integrals. I'm going to sort of trust you now to be able to do an integral like this. So let's do this inner integral on Sage just as a bit of review and maybe see the utility of Sage. So this inner integral is the integral of r cubed. So we want to integrate r cubed from r equals 0 out to 2 cosine theta, like that. Let me just double check. That looks good. So that yields 4 cosine to the 4th theta. So the inner integral is 4 cosine to the 4th theta. The outer integral, minus pi over 4 to pi over 4 of 4 cosine to the 4th theta d theta. Now, does anybody here know how to integrate cosine to the 4th? Honestly, I don't have it memorized, but I know how to figure it out. You have two paths here, and I'm going to kind of remind you of both of them. The first path is to go to the table of contents here and look at a table of integrals. So at the end of our book, there is a table of integrals. And if you go look at that table of integrals and scan down to the trig integrals, you see sine squared, sine cubed, cosine cubed, and you're like, yay, maybe I'll get sine to the or cosine to the fourth, but no, it kind of peters out there. But you do get cosine to the n, and you get a formula for that. And this is called a reduction formula. So let me grab that reduction formula and bring it back over into the notes and see if we can use it to help us with this integral. So the reduction formula says the integral of cosine to the n is this complicated expression. In our case, n is equal to 4. N equals 4. So what does that look like for n equals 4? It's 1/4 cosine to the 4 minus 1, which is 3, u, sine of u, plus the integral of 4 minus 1, 3 over 4, times the integral of cosine squared, u du. And you're like, great, Schuler, but there's still an integral there. But that's an integral that you should know how to do. That's an integral that uses the double angle identity. So we can rewrite cosine squared as 1/2 1 plus cosine 2 theta. Kind of running out of room here. Let me give myself some space. Maybe I'm not going to get any space here. Sadness. Oh, there we go. Okay. So it's got that half angle or double angle identity. I never know which it is actually. 1/4 cosine cubed u sine u plus 3/8. Take that 1/2, put it on the 3/4, plus the antiderivative here, theta, plus 1/2 sine 2 theta. All of that, oops, changed it from theta to like that, and that's also a u, apologies. That's the antiderivative of cosine to the 4th, and I'm supposed to plug in pi over 4 and minus pi over 4 and subtract. So we would do that and get 1/4 cosine cubed u, theta, sorry, sine of theta plus 3/8 u, sorry, theta, plus 1/2 sine 2 theta. All of that evaluated from minus pi over 4 to pi over 4. This 2 looks like a job for Sage. Let's go back over there and finish this calculation in Sage. We'll show, integrate, and we're going to integrate, what are we going to integrate? 4 cosine theta to the 4th power, and we're going to go theta from minus pi over 4 to pi over 4. Looks good. Turns out pretty nice. 3 pi over 4 plus 2. So that works out to 3 pi over 4 plus 2. Now, remember that this is the numerator. The numerator. What about the denominator? Well, you kind of have to start over again. It's a different integral, different stuff going on. R d theta is different from r cubed. So we just kind of have to start over again. I'm going to jump over to Sage, but I'm going to rely on you to be able to actually calculate this by hand. So let's do this whole integral again. We're going to integrate now r from 0 to 2 cosine theta, so we get that. And then we'll integrate the result, which is 2 cosine squared theta. from theta equals minus pi over 4 to pi over 4, and we get pi over 2 plus 1. So the denominator turns into pi over 2 plus 1, and the average value is 3 pi over 4 plus 2 divided by pi over 2 plus 1, whatever that works out to be. So that's the average value of the function x squared plus y squared over this region. Okay, for the following two exercises, we're given this spherical ring. I'm only going to do one of them. If the sphere has radius 4 and the cylinder has radius 2, we want to find the volume of what's left. And this is a great application of polar coordinates. What I'm going to do is I'm going to situate this figure by putting the hole, the opening, onto the xy plane and projecting the whole shape down onto the xy plane. So we're ignoring this guy. I'll let you do that one. In 164, we're going to put the cylinder with the whole side down, and what we're going to get is a pair of circles. So we've squashed this thing into the xy plane. And if you look closely at this, right, it's a sphere of radius 4. So this outer radius is going to be 4. That's the sphere getting smushed down onto the xy plane. And then the cylinder that cuts it out in the middle has radius 2. So that's cutting a hole inside. All right, we want to find the volume of the spherical ring. So we need to integrate from the surface above this to the surface below this domain of integration, like that. So the first thing we want to do is describe the domain of integration. That's not terrible. And in fact, I'm going to just focus, because of symmetry considerations, on the piece of the domain in the first quadrant. Because if you think about this shape, again, taking the circular opening, putting it onto the xy plane, it's symmetric above and below, and it's symmetric radially. So I can just take the volume of this shape over the green region, and in fact just above the green region, multiply by 4 to get all 4 quadrants, and multiply again by 2 to get the top and the bottom. So we'll take 2 times 4 times the volume above the green region. And that's a region that I can describe pretty quickly with polar coordinates. So r is going from 2 to 4, and theta is going from 0 up to pi over 2. Now, what's the surface? We're talking about the surface of a sphere. The equation of the sphere is x squared plus y squared plus z squared equals 16. If we solve for z, we get plus or minus the square root of 16 minus x squared minus y squared, like that. And since we're only interested in the part above the green region, we'll take the positive side of this. So the function that we're integrating is f of x and y square root of 16 minus x squared minus y squared. Now we have to convert that to polar coordinates, but we see our friend x squared plus y squared sitting there, and in polar coordinates this becomes f of r and theta square root of 16 minus r squared. So we'll drop that in as the integrand, 16 minus r squared. And then remember, in polar coordinates, we get r dr d theta. Cool. Now, this is a separable integral. We can do the theta integration completely independent of the r integration. If we do the theta integration, we're just going to introduce a factor of pi over 2 out here, along with the factors that we carried along because of symmetry. So this is 2 times 4 out here. And we just have to do the inner integral from 2 to 4 square root of 16 minus r squared r dr. But because we're using polar coordinates and because we get that extra factor of r, we've got a nice u du substitution here. U is 16 minus r squared. Du is negative 2r dr. Cool. We have an r sitting out there for us to use. So we're going to get, converting this, we're going to get minus, we'll kill that 4 with that 2. We're going to use this 2 in the u substitution, and there's an overall minus sign. So what do we get? We get 2 pi integral the square root of u times du. Now, what are the new limits of integration? Well, if r is equal to 2, u is going to be equal to 12. And if r is equal to 4, u is going to be 0. All right. Taking the antiderivative, negative 2 pi 2/3 u to the 3 halves. Let's switch the order of integration. So we'll change that to a plus, and we'll go from 0 to 12 like that. We'll plug those guys in, and we get 2/3. Oops, I forgot a pi, didn't I? There's a pi there. There's a pi there. I didn't forget a pi. We're good. 2/3 times 2 pi 12 to the 3 halves, and that's it. So that's the volume of this relatively complicated, let's call it a napkin ring. All right, and polar coordinates made this really easy. This would have been very challenging in rectangular coordinates. All right, last, not least, we want to find the volume that lies under the plane x plus y plus z equals 10, and above this disk, x squared plus y squared equals 4x. All righty. I'm going to get a drink. Hold on for a second. Okay, so we want to find the volume of the solid that lies under this plane. The first thing you need to do is kind of get a grip on what the domain of integration is. So in this case, we see x squared plus y squared equals 4x. And again, this is a complete the square, and we actually did this one earlier. Let me see if I can find it quickly here. This guy here. No, not that guy. Gosh, where was that? We did a lot of work today. Oh well, giving up. So we've got x squared plus y squared equals 4x. So that's x squared minus 4x plus y squared equals 0. X minus 2 quantity squared plus y squared equals 0. Oops. And when I complete the square, I've got to sort of pull off that extra factor of r, so minus 4 plus. Move that guy over to the right-hand side, we get x minus 2 quantity squared plus y squared. I think we're good there. Equals 2 squared. So it looks like we've got a circle of radius 2 centered at that point. See how terribly I can draw that circle. Okay, now we need to express this region in terms of polar coordinates, where we're integrating along rays that start at the origin and go out to the curve, right? Like that. Okay, so that means we need to find the equation of the curve in terms of theta, r in terms of theta. So what's the equation of this curve, r of theta? Well, we can go back to the equation up here and remember x squared plus y squared is equal to r squared, and x is equal to r cosine theta, and we can kill one of these factors of r, and we get it. We get r is equal to 4 cosine theta. So that's cool. R is going from 0 out to 4 cosine theta. All right, but what's theta doing here? What's happening with theta? It's not entirely obvious, but as I get close to the origin here, these rays get more and more vertical. And in fact, to cover the entire circle, the interior of this entire circle, I better start down here at minus pi over 2, and I better go all the way up to pi over 2. So the theta range is minus pi over 2 to pi over 2. Another way to see that is that's where, right, when you have theta equals 0 out here, theta equals 0, you're out here. Okay. When does this arc get to the origin? Well, it's going to start here at 0, and theta is going to increase and increase and increase, and the radius is going to go down to 0. When does it actually hit 0? When theta is equal to pi over 2. And if you go in the other direction, right, theta is decreasing, r is decreasing. When does r actually get down to 0 here? When theta is equal to negative pi over 2. So you've got to go through this. You've got to get a really solid understanding of the region of integration so that you can set these limits of integration. If you go past, right, if you wrap around, you're going to double count some of the area, and that's not a good thing. So you want the minimum theta range that covers the entire set. That's minus pi over 2 to pi over 2 in this case. Okay, now the volume of the solid that lies under this plane, that means we need to solve for z, 10 minus x minus y, like so. And we need to convert that to polar coordinates. So we get 10 minus x is r cosine theta, y is r sine theta, and finally, don't forget to multiply overall by r, dr, d theta, like that. You could actually break this up into separate integrals, each of which, I take it back, not with that theta sitting up there. You're just kind of stuck with this. So you integrate with respect to r, you integrate with respect to theta. I'm going to trust you to be able to do that. This integral with respect to r is just, right, r squared over 2, and you plug that in, and then you're going to get some trig integrals. Let's jump over, for the sake of time, to Sage, and we'll do one last example. We'll do it all in one fell swoop. We'll integrate both of these. We're going to go 10, the quantity 10 minus r cosine theta minus r sine theta times r, and we are going to integrate that from r 0 to 4 cosine theta. And boy, I have so many parentheses here, it's scary. There and there. And then theta is going to go from minus pi over 2 to pi over 2. And cross our fingers and hope that we've matched all the parentheses. Boom, 32 pi. All right. So that's polar double integration in a nutshell. I want you to move over and practice at least a couple of exercises in each of the major sections at the end, and when you've got things under control, go over to WebWork and try your hand at the Chapter 5, Section 3 assessment. All right, thanks a lot.